Okay, this is the second recording of the second theory class of AI504 because there was a bit of a technical issue in the morning's recording, so it wasn't actually recorded. So I need to re-record it from the beginning. So I might miss a bit. I might miss a bit of a detail. But I'll try to answer the questions asked during the morning class in Classroom. So this will be mostly just going over the slides, trying to remember what I talked about in the morning today, and then try to replicate what I did as much as possible. All right, let's get started. So this is week 2, basic machine learning, and So just to recap, for those who weren't there in the introduction class, the first week. So this is just going over the difference between AI and machine learning and deep learning. So more like not difference, but more like how their relationship is. So AI is anything that trying to make machines, computers mimic human intelligence. So it's not just deep learning. It's just anything that tries to, in any domain, any line of effort that tries to make machines or computers behave like human, like trying to make it look like they have intelligence. That's all artificial intelligence. So robotics is artificial intelligence. All the computer games that you play, they all have artificial intelligence component inside the software. So it's a concept as old as a computer because it started in the 1950s or 60s. So machine learning is a subset of artificial intelligence because there are other ways of trying to make machines look or behave intelligent, like expert systems. But machine learning is a subdomain of artificial intelligence where the focus is to use statistical methods to teach machines to learn from data to be good at a specific task. So tasks such as spam filtering, because machine learning, the rise of machine learning came about in mid-90s or like early 90s, mid-90s, when support vector machines were like all proposed and the following graphical models were proposed. So in that era, spam filtering was the representative example of machine learning. And the difference between like the previous methods, such as expert system, is that you no longer rely too much on human domain knowledge. For example, like you don't try to encode your human knowledge into the program. Rather, you use a set of a chunk of data, basically, for training samples, to be more specific. So you use training samples to teach a machine to learn a certain pattern to be good at specific tasks. So it's a statistical machine learning. And deep learning is even more narrower domain compared to machine learning. So deep learning is a subdomain of machine learning, and it is still a statistical method because you still need data to make the computers learn a certain pattern. But now the major difference between like classical machine learning and deep learning is that you use massive data and you use a big neural network model. And typically tasks are more complex than before. So before it was mostly just classification or regression. You try to guess the stock price, or you try to guess which is hen and which is spam. But now it's more complex, like translation or image captioning or question answering, those kind of things, or image, like style transfer, image generation. Those were all thought to be kind of impossible in the classical machine learning era, but now it is all possible thanks to a massive amount of data and a big sized neural network. And of course, powerful hardware is also really did a lot of help. So why focus on deep learning? So I think I also briefly talked about this before in the first class, but it's just, I think there should be, I think I'm missing a slide where I was trying to show the state-of-the-art performance achieved by deep learning models. But this is mainly just trying to say that the deep learning models require less feature engineering, because if you try to build a machine learning model, like classifier, a binary classifier that given an image, you try to guess or you try to make a machine classify whether it's a dog or no dog. So it's a binary classifier. And in order to do so in the classical era, you needed to extract, or you need to think of a certain set of features like these that makes dog look like a dog. So like a set of eyes, the color, the fur, nose, like does it have a tongue, does it have ears, and then you tell the machine, or you guide the machine to focus on this set of features to learn what it is, to what kind of pixel values form a dog compared to like cats or cars, so that your model can correctly classify dogs. So this should be no dog. And the deep learning, in the deep learning era, we don't need that much of human intelligence or human intuition. You just dump the pixel value directly into the machine so that the machines can learn what a dog looks like, basically. So but instead you need a lot of data, because you are basically forcing the machine to learn what a dog looks like on its own. So you need to provide a lot of samples, a lot of dog images, typically like at least like tens of thousands or maybe hundreds of thousands of dog images. So, but that's the basic philosophy of deep learning. You just provide a lot of examples and you pour that into the deep learning model, like large neural network model, so that it'll learn the features on its own. All right, so now jumping into today's main topic, the machine learning, basic ML, and typically people categorize machine learning into three different categories. So one is supervised learning, another is unsupervised learning, and the third is reinforcement learning. And some people, I guess some people would say reinforcement learning is not a category on its own, because it's a bit of it's not as it is not as popularly or often or largely studied as much as like supervised or unsupervised learning. But that kind of changed due to like AlphaGo and all that. Before, reinforcement learning was probably like a lot of people thought it was a dead-end study, but now it's made a flashy comeback because of the AlphaGo and the Atari and all that. So I would say that the three categories look okay: supervised learning, unsupervised learning, reinforcement learning. Looking at one by one. So what is a supervised learning? Basically, you're trying to learn a function. Learn a function that maps an input x to an output y. So it's a function, basically. So there's a function that you wanted to map properly the samples from your input domain to your codomain y. So if I can draw, if you think about your middle school days, the definition of a function is that there's a domain x and there's codomain y, and then there's a certain number of samples in your domain, and then you can map it to the points in your codomain like this. So maybe some samples are mapped to the same sample in the y domain, and then some are like going like this, some goes like this. So this is typically a function, and you're trying to learn a function that properly do this mapping between x and y. So it could be anything. For example, if we're thinking about image classification, or maybe let's say a dog or no dog binary classifier. So in that case, there can be only two samples or 2 points in the y domain. It is either dog or no dog. So it's a dog or a no dog, and there are images in your x domain, which is, let's say that your samples are 128 by 128. So your image has a resolution. Your image set of images are following the resolution 128 by 128. So your space, your domain x, is a 128 by 128 dimensional space, and the pixel values define different samples. So there can be like image here, a lot of like infinite number of images in your x domain like this. And then you want to map dog pictures, image of dogs to the correct classes, to the correct class in the y domain, the codomain. And if it's not a dog, if it's like a cat or a car or a bird, then you want all of them to point to, or you want to map them to a no dog. So this is basically a function, right? And definitely this is not a one-to-one function, because like a lot of different samples in your x domain is mapped to the same class in your y codomain. So it's definitely not a one-to-one example. I mean, basically you're trying to shrink your 128 by 128, which is about 16,000. So you're shrinking your 16,000 dimensional input to 2-dimensional input, which is just dog or no dog, right? So it can never be a one-to-one mapping, basically. So yeah, this is so yeah, you want to learn a function that correctly does. You don't want to learn a function that incorrectly maps your dog image to a no dog, right? Because that would be incorrect. So you want to learn a function that correctly does that. So the examples are image classification, French English translation, image captioning. Like if we're thinking about French English translation, then your X domain would be set of all the French words, like all the French words, I mean all the French sentences. So it'll be an infinite there will be infinite amount of samples in your X domain because there can be infinite amount of French sentences. You can always think of new French sentence, right? So there's no like limit to how many sentences there can be. And your Y domain would be English, set of all possible English sentences. English, French sentence, English sentences. And basically you're mapping certain French sentence to another certain English sentence, which is like the correct translation. So that's your function. Image captioning, then your X domain and your Y domain would be, your X would be some like the domain of images, like there will be infinite number of images, and your Y would be English sentence. So again, there will be infinite amount of English sentences in your Y domain. So you're just mapping a specific image to a specific English sentence. So that's supervised learning. Unsupervised learning is a bit different. So here we're trying to learn a function that where it learns the distribution or the manifold of the data X. So the distribution and manifold. So first of all, there's no label Y. So you just need to have the data X and that's it. So it's like you don't need like an explicit training samples where there's a input and the output, like X and Y. Usually people construct training samples in supervised learning, like manually by hand annotation, like human annotators. Like for example, like Amazon Mechanical Turks, they like annotate, they classify images using their human intuition, and that becomes your training samples. But in unsupervised learning, you don't need to do that. You just need to have a data, and then you're trying to learn a distribution of the data, or you're trying to learn a manifold to like make a compact space where the data lives. So in the morning session, I asked what could be like examples of unsupervised learning, and people gave me a lot of answers. I think there was clustering, there was generative models also. So we hear some people said generative models. Generative model. Some people said topping modeling as well. Topping modeling can be thought of like low rank approximation, low rank matrix factorization can be a form of topping modeling. So maybe there's some relationship there, here and here. So when I say manifold, so the reason that I use distribution / manifold is because if you learn the manifold, like if you, for example, let's say that you're using autoencoder. So there's an image, and so it's an image. So it used to be 128 by 128, but you're taking the rows and just appending it horizontally like this. You're taking here, and you're taking it here. So it'll be a very, very long vector. So let's say that this is your long vector. So it'll be 128. It would be 16,000 by 1. So it's just 16,000 dimensional column vector, and you're compressing it. So for example, let's say you're compressing it to 128 dimension, and then you're decompressing it to the original image, original space, 16,000 dimensional. And let's say that autoencoders can be thought of as unsupervised learning because it doesn't require an explicit label. It's just you just reconstruct you compress it and you compress your image and then decompress it, and the decompressed image you want that to be exactly the same as the original image. So that becomes your learning function. And when you do this, you're basically mapping your 16,000 dimensional original image to a 128 dimensional latent vector, or hidden lower dimensional representation. So in that space, you can think of the 128 dimensional space as more compactly holding or containing your images, because your images, like your there will be like infinite amount of samples in your original, you know, X space, which was 16,000 dimensional, right? And you are mapping it to 128 dimensional, Z space. Let's call it Z space. So this Z space is 128 dimensional, and there's like, you're mapping it to like different samples, different points in your Z space. So in that case, the dimensionality of your inputs, your images have changed from 16,000 to 128. So you're learning a manifold. You're messing, or you're manipulating the space itself. So it used to be the case that in the 16,000 dimensional space, your images would be sparsely located because it's such a high dimensional space. Your images are like, you know, scattered around. But if you compress your space into 128 dimensions, then you can probably think of like the entire space being like really compressed, really squishing the images to be close to each other as much as possible. So basically the distribution has changed from before. When it was 16,000, when the images were living in the 16,000 dimensional space, it used to be scattered. So it was like, you know, sparsely distributed. But now that you're mapping them to 128 dimensional space, they are densely distributed. So by changing your manifold, the distribution has also changed. So that's what I was talking about. That's why I use the distribution slash manifold function of this expression. So let's say that if you're only doing clustering using like something like k-means clustering, and you're not squishing you're not compressing your space, then you're only learning the distribution. So this is distribution only, this only. You're only trying to, you know, estimate how the data are distributed in your original space and which ones are close to one another, and you want to form a coherent cluster. So that's distribution only. But if you're doing low rank matrix factorization, then this is dist and manifold at the same time. This is mostly manifold and dist actually, because you're learning a manifold first, and then by doing so, you're automatically, you know, changing the distribution of the data. Kernel density estimator is learning the distribution only. You're using some like Gaussian kernels or something like that to, you know, to estimate how the data are distributed. So you want to learn a probability function in your space, so that you want to estimate like what's the likelihood or what's the probability of seeing a specific sample in your space. So it's that's KDE here, and the generative models are a bit different. I'll talk about that later. As I said, topping modeling, if you're doing topping modeling via low-rank matrix factorization, then you're doing both at the same time. All right, so yeah, so this is unsupervised learning. So additional, so just the caveat is, let me just talk about the generative models or autoencoders all at the same time. So generative models, for example, if you're talking about GANs, or let's talk about VAEs. So can you see VAE as an unsupervised learning? Because VAEs don't require an explicit label, because it's an autoencoder based model. So you only try to reconstruct what you see, what you want to compress your image, decompress it, and then, you know, you want that to be as closest to the original image as much as possible. So in that aspect, so let's call this X the original image, and let's call this X prime the output of your compression algorithm. And you want X to be as similar as possible. So you want the value of the difference between X and X prime to be as low as possible. So this is your label. So your X prime is actually playing a role of the label, but you haven't actually labeled it yourself. The label is coming from the data itself, right? So I think it's a bit awkward to call autoencoders or generative models as unsupervised learning, because there are clearly signals coming to you in your to your model. You need to train. You're training your model based on the input itself. So I think you can think of generative models or autoencoders to reside somewhere in between here. I think it depends on your preference, whatever you want to call it. Okay, we're moving on. Reinforcement learning. So reinforcement learning is even more different from the previous two, SL and UL. So it's still learning a function, but now there is an environment. So there's an environment here, and there's a set of actions, and then you're learning a function. You're learning a function that maximizes the long-term reward R. So if you think about playing the game of Go, which is Paduk, or Atari, the retro games. Let's use an example of Go. So for example, DeepMind's AlphaGo. So the environment would be the Go game itself. So it's a game. So this is Go. And then a set of actions is setting a stone on your board. And there can be many, many places where you can set a stone in the early stage of the game, right? And whenever you set a stone, you're working towards the end stage of the game. So the reward is, of course, either 0 or 1. If you win the game of Go, then you get a reward 1. If you lose the game, you get a reward of 0. And by choosing a sequence of actions, by setting stones, you want to win the game eventually. So it's a long-term reward. You don't get a reward as soon as you set a stone. Only after you've set enough amount of stones on the board, then you can see whether you've won or lost the game. So it's a long-term reward. So you want to learn a function that chooses a optimal set of actions so that you can win the game, or you can maximize the long-term reward when you're when you're like moving around in your environment. So examples are Go, Atari, like any computer games can be, any game actually. It's not just board game, like board games, computer games, whatever. They can all be interpreted in terms of reinforcement learning. And self-driving car as well. I think self-driving car can be a good example. So your environment is the street, the world itself, and your set of actions is turning your wheel handle, or stepping on the gas or braking, and the reward is given to you if you've reached your destination. So you start from your home and you want to go to your job, right? You want to go to your office. So only driving safely and as accurately as possible. And if you arrive at your office, then you get a reward of 1. And if you just crash into somebody, or if you go to a different place, then you get a reward of 0. So that could be a good example. All right, moving on. So this is the 3 categories, and I just want to say that in the modern deep learning era, the line between SL, supervised learning, and unsupervised learning is a bit blurry, especially because of the models that I just talked about, autoencoders or generative models, or even self-supervised learning as well. Because if you think about BERT, so anybody who's not familiar with BERT is basically how you train the BERT model is you give a sentence. So there's a big giant model called BERT, and then you give a sentence like, I like to play with my dog. And then you just randomly remove a certain portion of your words. So for example, let's say that you remove this, and then you remove this, and then you put these into your BERT model. So they will be something called mask. And then you'll get a same number of outputs from the BERT model. So this will be, I like to something with something dogs. And you want your model to correctly predict what the erased tokens were. So basically this should be play. This should be my. So you, as again, like the autoencoder example, the labels are coming from the data itself. You don't need human annotators to manually annotate the Y labels for this input, because this input used to be a complete sentence, and you just randomly remove certain portion of your sentence, and you're trying to force BERT to reconstruct or predict this original identity, right? So you don't need a separate label. So this is again kind of like similar to autoencoders in that sense. And in that sense, I'm not sure whether we can call BERT or self-supervised learning methods as unsupervised learning or supervised learning. I think it resides somewhere in between these two. All right, moving on. So this is the 3 machine learning categories: supervised learning, unsupervised learning, reinforcement learning. And I think all practices in this course are either SL or UL. So if you consider GANs or VAEs or autoencoders as unsupervised learning, then yes, all practices in this course are either supervised learning or unsupervised learning. Reinforcement learning, we don't do that here, but if you follow the course very closely, and if you do all the practices, and if you can pass the class, then you'll have a better time, easier time implementing your RL agent models in the future. If you're interested in reinforcement learning, you can take deep reinforcement learning class provided by the Grad School of AI. I'm not sure if it's open this semester, but it's definitely open at least once a year. All right. So we're moving on to the optimization domain. So whatever you do, whether you do SL, UL, or RL, you need to train your model. So there, I said that all of them, this, and this, they all try to learn a function. In SL, you're learning a function that maps X to Y. In UL, you're learning a function that learns the distribution of X. And in RL, you're learning a function that correctly chooses a set of actions to maximize your reward. So it's all function learning. And in other words, you're training your model. So learning a function is training your model. It's the same thing. This is equivalent to learning a function. Learning a function. So, and you need your machine needs to learn from data. So training your model or learning a function, it is done based on the data, because it's still a statistical method. So everything, all the machine learning methods in this class is all statistical methods. So you need to have data, and you need to, based on the data, you're training your model. So that's why it's called statistical machine learning. You're training your machine from the data. So it's statistical machine learning. So how to train your model? So a cute picture here, right? So how to train? Well, you have a function, so you need to know how to train your model. So how to train your model? How to train your model is your model is a function, as I said. So you can denote your function or model as fx semicolon theta, because your function consists of weights or coefficients. For example, if your function is like w1, w5 x to the 5, w4 x to the 4, yada yada yada, w1 x to the 1 plus w0. So this is your function, right? And then your function will have a coefficient or learnable weights, which is here, 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 here. So weights or parameters are usually denoted by w or theta. So theta denotes all set of parameters in your function. So how your function behaves, it's determined by the parameters. And how to train your model. So that basically, how to train your model is how to learn the correct set of parameters, the parameter values. And in order to train your model, you need to have a goal. So if you don't have a goal, you don't know how to train your model. If you're like when you're training a dog, if you want your dog to sit, then that's your goal, right? Trying to teach your dog to sit. So if you want you need to have a specific objective to train your model. So we call this goal an objective function. So you need to have an objective function to train your model. And for example, let's go back to the dog classification example. So binary classifier, we're trying to model, or you're trying to train a binary classifier function. And the classes are either dog or no dog. And the objective is correctly classify, not the digit, sorry. So it's not the digit. Correctly classify dog or no dog. So that's your objective. Given an image, you want to correctly, map your input, which is coming from the image domain, to the class domain, which consists of two samples, dog or no dog. And in order to do so, you need to define something called loss. So your objective is to correctly classify, and loss is something based on the true label and your predicted label. So your predicted label or your prediction from your function is coming, of course, it's coming from your function. So your function predicts some class. It could be dog or no dog. And based on the true label, which is coming from the data, the training data, you can calculate the loss. For example, if this is dog and you say, and unfortunately your model said no dog, then there should be some penalty, right? Because it's you lost the game. You're not really achieving your objective. So that's why it's called the loss function. So you want to minimize the loss, basically. In order to achieve the objective, you need to minimize the loss. And typically, loss in binary classification, the loss we use most of the time is cross entropy loss. So here, this is called, from here to here is the cross entropy loss. cross entropy loss. So let me just dive into it to interpret what's happening inside. When you use cross entropy loss, what does it mean? How does using cross entropy loss really help you achieve your objective of correctly classifying a dog? So your y, your true example, so let's just look at one term by, I'm just gonna write it here, y log y hat, which is your prediction, plus 1 minus y log 1 minus y hat. And I'm just going to ignore the negative sign here. There should be a negative here. I'm just going to ignore it for now. So what happens is your y is either 1 or 0. So 1 being dog, 0 being no dog. So your y is either 1 or 0. So when your y is 1, then this term goes away. So you only have this term around, right? So as I said, that your y is 1, so you only have log y hat. And y hat is typically, y hat can have the value between 0 and 1 because you're using a binary classifier. So your classifier doesn't predict 0 or 1, predicts like some like continuous value, like 0.5, 0.777, 0.892, something like that. So your y hat would be a float value that resides between 0 and 1. So what happens is if the true label is dog, then what you want to do is you want your y hat to be as close to 1 as possible, because the true class is 1. So you want your y hat to be 1, and your log y hat, the function looks like this. So if you draw a function, this is 0 and 1. This is your y hat, and this is your log y hat, right? If your y hat is not 1, so your log y hat can only have a value between here and here. So it's either negative infinity or 0. So only when your y hat is 1, your log y hat would be 0. Otherwise, it's all negative values. So in order to, you want your y hat to be as close to 1 as possible. So maximizing this term automatically, leads to maximizing the y hat value, because log is a monotonic function. So maximizing this function leads maximizing this, or leads to maximizing this, and that's what you want when your y true label is a 1. In another case, when your true label was 0, so it's an image of a node. It's like, let's say it's an image of a cat. So your true y is 0. In that case, this term goes to 0, and only this term lives. So since y is 0, this term becomes 1. So you're only left with log 1 minus y hat, right? So in this term, you want to minimize your y hat. So you want your y hat to go to 0. So that's why there's 1 minus y hat. So it's different from the previous term, which is y hat. So you want to by maximizing this, you're minimizing this, right? So that's how cross entropy operates. So you can divide your cross entropy to 2 cases: the positive case, the negative case. And both times you're trying to force your y hat to be as close as possible to true label. And because it's called loss, so I said that either maximizing this or this helps your model to achieve your objective, correctly classifying the image. But since maximizing this is I'm trying to interpret this as a loss function. So by putting negative in front of this entire thing here, this makes it a loss function, because now if you minimize this, then you're maximizing this, right? So the loss function, it's a loss, right? So you want to minimize your loss function in order to achieve your objective. So minimizing this entire thing leads to maximizing the inside here. So that's how the cross entropy loss operates. And of course, there are other loss functions, because this was a binary classifier. So binary classification. For this, you use cross entropy. But for other tasks like multi-class classification or regression or something like that, there are different loss functions. So we'll get to that later. Yeah. So you need to find. So now you understand the loss function. So once you've defined your loss function, you need to find theta that minimizes the loss function. So loss function is a function determined by theta. Theta is the only variable here because x and y, here and here, this is determined by your training sample. So they're fixed. So x and y are fixed because it's given to you. The only thing that you can control is the theta. So if you think about a loss function, for example, let's say that your loss function looks like this. So this is your loss y comma f x semicolon theta, and it is only controlled by your theta value. So the once you have minimized your loss function, that's when you've achieved your objective. So you need to find a theta here, 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 here. You need to find a theta that minimizes your loss function. So obviously that would be here, because out of all like, you know, possible values that the loss can take, this here is the minimum value achieved by this specific theta star. So you need to find that theta star so that you are achieving your objective. So, and you know, minimizing a function or maximizing a function, it's called optimization in the optimization theory. Like, you know, people from industrial engineering would be very, very familiar with this. So we call this optimization. You have a function and you want to minimize it, or you want to maximize it by controlling the parameter. Optimization. Moving on. So as I said, there are other loss functions. It's not just cross entropy all the time. So for when you're doing regression, there's something called mean squared error, or there's mean absolute error. I won't go into detail, but we might you know, run into them when we're during the practice sessions actually. All right, moving on. So how to optimize your model? So as I said, we have defined what optimization is. So we have defined the objective function and we have defined the loss function, and we know what optimization is. Optimization is basically trying to find the theta that minimizes your loss function. So let's just, you know, trace back. So find theta star leading to minimizing your loss, leading to achieving your objective, again, which leads to learning successfully learning a function, or maybe same thing, training your model. So that's all. It all boils down to this. So we started from here, top down. We wanted to train a model. We've defined the objective function. We defined the loss function. Then it all boils down to this: finding the right theta. That is how you train your model. So, for example, let's say that your function is so simple. It says x squared negative minus 2x plus 1, which is basically what? X minus 1 to the squared, right? So if you can draw this, it's all like, you know, all high school. It looks like this. This is 1. Actually, this is also 1. 1. This is 0. So what's the minimum value that this function fx can take? It's 0, right? Because this is minimum value. And when does it become minimum? Well, like if you remember, what we did to find the minimum value in the polynomial functions was that you take the gradient, you take the derivative function. So you differentiate fx into f prime x, which is 2x minus 2, and you set it to 0 so that x becomes 1, right? That meant that when you set your x to 1, that is your minimum. So f1 is the minimum. F1 is the minimum value of fx. Why is that so? Because why do you do this? Why do you do the differentiation, and why do you set it to 0 and try to find the point where the gradient is 0? It's because when the gradient is 0, that's when your function has become, has reached rock bottom. So that's the minimum value. Because in all other points, the gradients are non-zero. It's either positive or it's negative. But here, in the lowest part of your lowest point of your function, that's when your gradient, that's when the function's gradient becomes 0. So this, and we call this global minimum, because there's only one minimum. This is global. So the opposite of global minimum, and it's not opposite. Like, for example, if you can think about a function like this, there are two minima. There's one here and one here. So, but obviously this is lower than this one, right? So this becomes the global minimum. and this is just a local minimum, right? So, but in a quadratic function, x squared, there can be only one minimum to begin with. So your local minimum is your global minimum in a quadratic function. But in higher order polynomial functions, there can be multiple minima, local minima. So this is a local minimum, this is local, like this and this and this, they all become local minima, and you don't know which one's your, I mean, you have to, kind of find out which one's your global minimum. There can be only one global minimum, but there can be many local minima. All right, so in this spirit, so the setting the gradient to 0, and then using that point where the gradient is 0, using that point as your minimum value, that's kind of reasonable, right? That's what we did in the high school days. But if your function is not just quadratic function, but your function is like convolutional neural networks or recurrent neural networks or transformers, then your function is so complex, there's no way you can find the global minimum analytically. Like you're solving your functions like this, and then trying to set it to 0, and like doing like algebraically manipulating your function and then trying to find the minimum. It's no longer possible when you're dealing with like transformers, like gigantic big deep neural networks. So yeah, no analytical solution, and there are many local minima, because gigantic functions, if you put so your loss function would look like this. So y f x theta, and if your f is like a really like millions of dimensional function, having like millions of parameters or even tens of millions of parameters, then it's a very high dimensional function, and your loss geometry will be also like very high dimensional. So there can be millions, and maybe even trillions of local minima, and you don't know which one's global minima. So there's no analytical solution. So if there's no analytical solution, then you need to find it numerically. So so iteratively. So for example, if your loss function looks like this is your theta, and this is your loss y comma fx theta. I mean, this is rather simple. This is only what is this? This is fourth, like I would say, need to erase a bit. So this would be fourth order polynomial function, but let's say that you're trying to find the local minimum, find the global minimum, which is here, theta star. Let's say this is theta prime. This is a minimum, but it's a local minimum. It's not as low as this point, right? So what do you do here? So what you do is, how many points are there where the gradients are 0? There are 3 points where the gradients are 0, right? There's one here, and one here, and out of 3, which one do you take? So you don't really know. I mean, if you can draw it like this, you can easily know. But if you can't, if you're dealing with multidimensional function, it's really hard to imagine or draw or pinpoint a certain point where the gradient is 0 and also the point is global minimum. So you first randomly choose some point theta 0, which is your initial point, and then you take the gradient, and then you go down the slope until your gradient becomes 0. So because here the gradient is not 0, so you go down, and then at some point your gradient will be 0, and then that's when you know that at least you achieved local minimum. You don't really know if it's global minimum, because, for example, what happens if your initial point was here? What if this is your initial point? Then you take the gradient, you go down the slope, you go down, you slide down, and now your gradient is 0. So I mean, once you've hit gradient 0, there's like you're kind of satisfied with your local minimum. So you don't really know, unless you risk going upwards and then going downward again. There's no way to find the global minimum. So typically you just you start from somewhere random, you just choose a random point, and then iteratively go down the slope until your gradient becomes 0. And then when your gradient becomes 0, you kind of assume that you've hit a good minimum spot, and then you stop your optimization process. So that's what the gradient descent is actually. So here, yeah, I just talked about the gradient descent. So what gradient descent is basically going down the slope. So you pick a point and then you just go down the slope until your gradient becomes 0. So this is a concentric circle. So you can think of a quadratic function like this. So this here line is like here. And there are a lot of heights or depth. So this is here, this is here, this is here, this is here. Well, like this. So it's a concentric circle of like altitude. And you're starting from here, basically. You're starting from here. So this is your theta 0. And then once you've started here, you take the gradient, you go down a bit. You take a small step. You take like a many number of small steps, because you don't want to go too much. Like if you go like this much, then you're actually overshooting your spots. So you don't want to do that. So you want to take a small step, and then you see where you are, and then you take another step, see where you are, calculate the gradient, take another step here, take another step, take another step. Like you go down, 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 taking a very small step, and then at some point, when you're here, your gradient will point here. So you take another step here, and then you reach the global minimum, which is this point. So that's what gradient descent is. So you're taking the gradient of your loss function. This is a loss function. So this is loss. You're taking the gradient of your loss function with respect to the theta, which is the only controllable parameter in your loss function. And then you're taking the derivative, and then by then the gradients, the gradient of your loss function will be a vector. It'll point to some direction, right? So you go to that direction like iteratively. You go here, 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 taking small baby steps. So this determines this eta term here determines how large your individual steps are. So you go down, and you go down, and then you go down, and hopefully at some point you will reach here, the minimum. And I mean, again, there is no guarantee that this is a global minimum, because there can, if you go, there can be another concentric circle here, and then at some point it'll be like this. So it just, let's say if this was the global minimum and this is just a local minimum, unfortunately you just happen to start from here, and that's why you reached here. If you're lucky enough and you started from here, then you would go here, right? So whether you reach global minimum or local minimum, it all depends on luck when you're using gradient descent. All right, so that's gradient descent. And stochastic gradient descent is a variant of gradient descent. So let me just erase all of this. Here, the gradient was, I said that the only controllable parameter in your loss function was theta, and y and x are coming from the training samples. So here, the gradients are calculated such that you take, there's loss function, there's individual loss function for individual samples. So there's like y1, the first sample, x first sample, comma theta. Then there's another loss function for your second sample, y2, fx2, theta, and then there will be a lot more of these. So loss yn, comma fxn, semicolon theta, right? And then if you do a gradient, if you take the gradient, then there will be n number of gradient terms, and you add them all together, or maybe you can do average them as well. So you just you need to merge them all together. You're collecting the gradient information from all your training samples. So you're not leaving anyone out. You're just taking you're just looking at all the samples and then taking the gradient, and then you're merging them, and that's how you decide the direction, future direction. But in the stochastic gradient descent, you're not using the entire thing. You're using a subset of training data. So this y here and x here, it's not your entire data. It's using a subset or mini batch of the entire data. Like it could be 64 samples out of like billion samples. It could be 128 samples, 256 samples. It depends on your choice. So why use SGD? That's because, first of all, your training data is too big. So if your training data consists of millions or maybe trillions of samples, there's no way you can fit all of them into your memory so that you can calculate the gradients. And of course, time consuming as well, because you need to go through all the samples one at a time until you reach all the million samples, and then calculating the gradients, and then merging them together. It's just, there's not enough time, there's not enough memory, so it's just impossible. So this is the realistic, this kind of like the realistic reason why we use SGD. And sometimes smaller batch size helps avoid suboptimal minimum. So I said that whether you reach global optimum or local minimum, I mean global minimum or local minimum, it's all kind of luck. But sometimes if you use smaller batch size, it kind of helps you avoid local minimum. So let me draw a scenario. So when you're using your entire loss function, entire training samples to calculate your loss function, for like this, your loss geometry, your loss function might look like this. But if you use a subset of y and subset of x, then let me erase it a little bit. Then if you use a subset of y, so maybe like y ends and f, like only n number of samples in your entire training data, then your loss function geometry might look like this. I mean, this is all theoretical. There's no guarantee that it will look as nicely as this, but theoretically, there could be scenarios where this is true. So here, for example, let's say that you started from this point. This is your theta 0, and this is your theta star, right? This is where you want to go, and this is your initial point. If you're using the entire y and x samples, then you are actually drawing the true geometry of your loss function. And unfortunately, your true geometry of your loss function is so wiggly that you might end up being here in the local minimum when the true global minimum is here. But if you use a subset of your training samples, then your geometry is an approximation of the true geometry. It's an approximation. So it might be just the case that it is so beautifully looking like this. So you start from here, and then you can maybe you can reach to this point eventually to the star, because you're using like it's like trying to perturb your geometry a bit. So it's like adding noises. So sometimes that might help build a robust model. So that's what this is what I'm trying to say in this sentence here. Sometimes it helps. And another question is, well, if we use SGD because of the realistic reason or maybe because of theoretical reason, I mean, how can we be sure that SGD will give me the same theta star as GD? Like, how can we be sure that SGD, like if we use SGD, it'll give me as good model output or parameter values as using the full GD? Well, there's a theory. It is already proven that if your mini batch samples are sampled independently and identically, basically randomly, if you sample your mini batch, so this is your entire data. Oh, sorry about that. If this is your entire sample, and then you try, sometimes you sample here, sometimes you sample, like this is your mini batch 1, this is your mini batch 2, mini batch 3, mini batch 4. You just randomly sample, not even like a cluster. Maybe you sample from here, 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 here. Like if you randomly sample your mini batches, and then you run SGD for infinite amount of time, then it is actually the same as GD. So that is already theoretically proven. So that's why we can trust SGD to some extent. So yeah, so modern deep learning is all founded on SGD. So the optimizers that you often see, such as AdaGrad or ADAM, they're all like variants of SGD. They're more advanced version of SGD. All right, moving on. So evaluation. So how do you know when to stop SGD? How do you know when to stop optimizing your model? Or how do you measure how good your models are? So because you can't run SGD forever. Like at some point you have to stop, right? So because we're using loss function to optimize your model, you can actually calculate how much loss your model is making, because loss function, the cross entropy is a function. So you can, using your current parameter values and using your X and Y mini batches, you can calculate your loss value. And hopefully your loss value will decrease and decrease and decrease as you update your parameters, right? Because you're trying to minimize your loss function. But using your loss value is not very intuitive, because loss, like what does it mean to have a 10 to the negative 3 for your cross entropy loss. Like if your cross entropy loss is 10 to negative 3, what does it mean? Or what if it's 10 to negative 4? Like how do you know when to stop? Like, well, how do you know? It can't, you can't run it forever so that it'll be like 0. Your loss function will never be 0 actually. So how do you know when to stop? So that, because just relying on loss value only is kind of, not very intuitive. That's why we have popular evaluation metrics like accuracy, AUROC, precision recall, blue score, perplexity, FID score. So these three are a bit for specific purposes. Blue score, we usually use it for machine translation. Perplexity, we use it for language modeling or text generation. FID score, we use it for image generation, like GANs. And these three are, I guess this used to be, popularly used in information retrieval, but it is sometimes used in classification as well. If you're doing binary classification, this is the go-to method. I mean, go-to evaluation metric. If you're doing multi-class classification, then accuracy is probably a reliable evaluation metric. Assuming that your classes are evenly distributed. Like if you have if your classes consist of like car, cat, and dog, and in your training data there are 1 million dogs and 1 cat and 1 car, it's not an evenly populated data set. So in that case, it's not a good data set to begin with, and you can't use accuracy. So given that your multi-class classes are evenly, at least reasonably distributed, accuracy is very reliable. All right, so yeah, so instead of using the loss value, you can use like these kind of like popular methods to understand how well your model is doing. Right, now, train and validation test set. So when you're optimizing your function, when you're running SGD for your model, you want to split your entire data set into 3 data sets. So there's one training set, and there's validation set, which is usually called development set as well. And then there's test set. So if you train your model on training set, and then you evaluate your model on the training set, that is basically cheating, because you are exposing your model to a training set, and then you're trying to evaluate your model on the exposed data set. So in that case, it's too easy for your model because your model has already seen those training samples. So in order to truly evaluate how well your model will generalize to unseen data set, you need to have a separate test set. So this is what that's for. So during the optimization phase, or when you're training your model, you never provide your model the test set. So this needs to remain unseen. And then so these two you can use during your training phase. And once you train your model, and then you use validation set to evaluate how your model is doing, using like accuracy or AURC or precision recall, whatever you like. Using some metric, you evaluate your model against validation set. So it's kind of like a proxy for your test set. Because you can't use test set because it needs to remain unseen, you use a separate validation set that is different from training set. So training set is what you use to calculate the gradients and do gradient descent. Validation set is only for evaluating your model from time to time. So you can use this set to evaluate your model and decide when to stop training. So once you've reached like satisfying evaluation score on your validation set, then you can stop your SGD training. And then after that, only after you've finalized your model, then you test your model on the test set to see how well it will generalize to unseen data set in the future. So important thing, don't ever use this set during your training phase. So we come to something called n-fold cross-validation. So for example, let's say that you have the entire data set. Let me actually redraw it in the black color. So let's say that you have a entire data set, and then you took 80% to be a training set and the validation set, and you take the remaining 20% to be the test set. So this is the unseen set. And somehow, by luck, or fortunately, or maybe unfortunately, your test set was really simple cases. So your model trained on this portion was doing so well on your test set because it was just, it just happened. It just so happened that your test set consisted of only really, really simple cases. So your model was like scoring 100% test accuracy or 100% test precision and recall or something like that. So in order to avoid this kind of biased, evaluation, what we do is n-fold cross-validation. So what we do is, for example, let's say that you split your data into 8 segments, and in one training phase, you use the first segment as the test set, and you use the remaining 7 as the train and validation set. In the next segment, you use this as a test set, and you take the remaining this and this as the training and validation set. And in the next phase, another phase, you take this as the test set, and then it's repeat, doing the same thing. So you do this for the 8 times, because there are 8 segments, 1, 2, 3, 4, 5, 6, 7, 8. There are 8 times, so you need to do this 8 times to do 8-fold cross-validation. So if you do this, then you don't run into these lucky cases or unlucky cases. If you do this a lot of times, if you do 8 times, then you can safely say that your test set was not biased that much, and your model's test accuracy or test performance can be trusted, to some extent. It's like doing this 8 times is way more reliable than just doing this 1 time. So that's where n-fold cross-validation is. But these days, in modern deep learning, this n-fold cross-validation is not very often used, because first of all, your data set is so large, it's just unreasonable to do n-fold cross-validation when your data set consists of like millions or trillions of samples, because just training your sync model 1 time using 1 split takes about at least a couple days, or maybe several days, or even like several weeks. And you don't want to do that n times. That will take months to calculate the n-fold cross-validation. So you don't want to do that. So that's why, first of all, that's a realistic reason. And another reason why we don't do n-fold cross-validation these days in deep learning is because the test set is too large. It's so large that it's already kind of reliable. So this lucky or unlucky cases where the test samples are really easy or like really hard, this can only occur when the test samples are small. Like if you use only, maybe like, for example, if your entire data set consisted of 100 samples and you use 20 samples for your test set, then it could be the case that 20 samples are like hard cases or simple cases. But if your entire data set was like 1 million, then your test samples are 200,000 samples. And that alone is already too big to think about biasness or anything. So it is already a good representation of unseen data set. So in this case, you don't really need to do n-fold cross-validation to get an unbiased generalization performance. So that's why. So it's time-consuming and statistically kind of unnecessary. All right, moving on. Right, so now we go to overfitting and underfitting. This is a classical topic in machine learning. So the lesson here that I'm trying to convey is that you need to think about how complex your data is, and how expressive or how powerful you want your model to be. So this is kind of determined. Like you already have a training data, so you can't really control the complexity of your data. Oh, I'm sorry, you can actually, because you can add more features, but that doesn't really count in deep learning era. So anyway, let's just set that. I think it's safe to say that your data complexity is more or less fixed, but what you can control is your model capacity. And by capacity, what I mean is how powerful your models are. For example, if your model is theta 2x squared plus theta 1, x1 and plus theta 0, compared to fx theta 5 x5 x to the 5 plus theta 4 x to the 4 plus yada 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 theta 0. Compared to this, compared to this function, so this is, let's say this is f2, this is f5. So compared to f2, f5 is more expressive because it can fit more complex line, because this is a quadratic, so this function can only fit lines looking like this. But here, f5 can actually, it's a superset of f2, because if you erase if you set theta 5 and theta 4 and theta 3 to all 0, then this becomes this, right? So it's a superset of f5 is a superset of f2. So it has higher capacity, or it's more expressive, or it's more powerful. So that's what you can control, like how powerful model you want to use. Or if you think about, transformers or BERT, how many blocks you want to use in your transformer model. That's also, controlling the capacity of your model. If you want to use 12 blocks or 24 blocks or 36 blocks, that's controlling your model capacity. So why am I talking about this? Let's look at the first figure. The true sample, training samples is distributed along this kind of orange line here. So this orange line is the true data distribution, and your data is distributed or kind of scattered around this orange line. There are some errors, like there's you put some noise when you're generating the data, so there's a bit of a distance between the true line and the samples. But anyway, you can see that they're scattered around this. And when you use a polynomial function of degree 1, it is too low capacity. So when you fit your function, degree 1 function, to fit this data, the best it can do is this line. And it is not really fitting that well. You can see that the distance between the line and the samples are quite large. So, the gap is pretty wide. So you can see that it is not fitting very well. And not fitting very well means underfitting. So this is what underfitting is. If you use just the right power for your model, which happens to be degree 4, then you can see that the true orange line and the approximated or the fitted blue line almost coincide. They're like almost overlapping to one another. And in that case, the distance between the blue line and the actual samples is kind of minimized. So it is fitting pretty well. But if you use a too powerful model like degree 15 polynomial function, then it is trying to fit exactly to the data. So here, 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 like here, 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 here. Because your model is too powerful, it is responding to every single small perturbation to your sample because of the small error here, the small noise here, small noise here, small noise here. It is responding to that small noise. So that is why the blue line is so wiggly and weird looking like this. So it is trying to fit the training data too perfectly. So let's say that you have this blue lines are the blue dots are your training sample, and you happen to input some test samples along this part of the orange line, like here and here. So let's say one here, one here, one here, 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 here. These are your test samples. About the same place here. About the same place here. So in all three cases, the gap between the blue line and the test cases is pretty large, right? It's pretty large. Here it's minimized because we're using the right amount of power for your model. Here is so vast. It's so the gap is just it's just crazy. It's because you're using a too powerful function, so it is overfitting. So this is what overfitting is. It is overfitting to your training samples to the extent that it is not generalizing well to unseen cases. Unseen cases being here. So the lesson is you need to use the right amount of power for your model. And you can see this happening when you're actually training. So doing too well on your training data doesn't always lead to good test performance. So achieving 100% accuracy on your training sample doesn't guarantee that you'll get 100% accuracy on test samples, because as I said, test samples are unseen cases. So you can't guarantee that. You can't guarantee that doing well in training data leads to doing well in test data. So that means that it does not generalize well to unseen data. So this is your model complexity. So this can be your polynomial function of degree 1. This is polynomial function of degree 2, degree 3, and this is degree 4 in the previous slide. This is degree 5, and somewhere here it will be polynomial function of degree 15. So your model complexity or your model capacity is growing, and this is your error. This is your loss. So if you use too simple function, then your training error or your training performance and your test performance will be bad altogether. And as you increase your model capacity, your training performance or your error on your training set will decrease like this. It'll go down. And if you keep pushing, then at some point you'll reach like 100% accuracy on your training set, because now it is overfitting to every single detail here and here and here, right? So your training set will be minimized, but at some point your test set error, your test performance will decrease. It'll degrade because you're using too powerful function. So you need to find a sweet spot, which is f to the power of, which was the polynomial function of degree 4. You need to find just the right balance for your model capacity or your model power to reach to get the best test performance. And how you do that is kind of like, it's more or less heuristic, or you can use some techniques that I'll introduce in the future slide. So yeah, this is the whole gist of overfitting and underfitting. All right, moving on. So the previous example was regression, because you're trying to fit a line, but you can reiterate the whole underfitting and overfitting thing in the classification example, and also in the deep learning there can be also deep learning interpretation. So in regression, this is quadratically scattered or generated samples, and you're trying to fit a line which won't work. So this is underfitting. This works just well, and if you use like degree 15 function, then it'll just respond to all the every single training samples in your training data. So this won't generalize well. Same can be said in the classification. So this is the red area, this is the blue region, this is the red region, because there's a boundary here. So this boundary separates from the blue side and the red side. And here currently, because we're using a line boundary, there's a lot of errors in here. There's some error here, but there's a lot of error here, and here and here and here. If you use a quadratic function or quadratic boundary, then your boundary looks like this. And now there are less errors than before. So there's error here, and error here and here. So it's way less number of errors than before. But if you use a too powerful model, then it'll try to get every single sample correct. So that is why you have this weird looking boundary like this, right? And clearly this won't generalize well, because, for example, in the future, maybe your training samples will be here and here and here and here and here and here. In that case, like all the region here will be all errors in the future. So this is the sweet spot. And in deep learning, instead of actually visualizing like this, what you can do is you can look at the training phase. So as you keep training, as you keep running your SGD on and on and on, if your model is too restricted, if your model power is too low, then both your validation error and training error will be kind of high. It's a high error. If you're using just the right power, then your both validation error and training error will be low. So it is lower than before compared to this and this. But if you use too powerful model, then your training error will be it'll be 100%, because it'll be 100% accuracy, because like this, it is just responding to every single detail. So your training error will be minimized, but your validation error will be higher again. So as I said, validation error is different from test error. Test error is something you have never seen before. Validation error is a separate data set from training set that you use to evaluate your model during your training phase. So it's a proxy for your test set, and you can see that it is increasing again when you use a too powerful model. So that's how you can kind of like approximate your model capacity, whether your model is overfitting or whether your model is underfitting in the deep learning regime. All right, so how to overcome that? How to remedy underfitting and overfitting? So there are certain things that you can do. So first of all, when your model is underfitting, so I'm just gonna erase all this. When your model is underfitting, what you can do is you can complexify your model, which means that just adding more complexity to your model, or you can add more features. So this is important. So in these days, you don't really do a lot of feature engineering, but back in the machine learning era, for example, if you're doing dog classification, again, back to the dog and no dog scenario. So there's a image of a dog. And let's say that initially you only use the eyes as your feature. So the initial features were only eyes. And of course, if you only use eyes as your feature, then it won't do really good job because cats have eyes, humans have eyes, like like bears have eyes. Everything has eyes. So if you use only eyes as your feature, then your model won't be able to classify dogs from no dogs that well. So what you can do is you can add more features. So your next set of features can be eyes, maybe whether it has furs, whether it has nose, whether it has ears, how is the color. If you use this combination of features, then now your model can actually classify or distinguish between dogs and cats and humans and bears, because first of all, humans don't have furs, so and cats have different type of fur than dogs, and so like giving more information to your model basically helps overcome underfitting. But there's like trade-off between using too many features and using too small features, but we'll get to that later. Remedies for overfitting. What you can do is basically regularization, which I'll get to later, or more directly, intuitively, you can get more data. That always helps overcome your model overfitting. Why is that so? That's because if you add more data, like if you just try to make your sample space really, really dense, like this, really, really dense, and then there will be a lot more reds here, like this. There might be some red arrows here, there might be some reds here, and there might be some blues here as well sometimes. But since there are so many reds and so many blues, it's impossible for your model to actually wiggle through all these things and get the 100% accuracy when there's so many data. So it's like sooner or later your model has to compromise between getting a decent performance and trying to overfit your training data. It's just impossible when it's just impossible to overfit when your training set is so massive. It's just impossible to wiggle through all that small small space to overfit to very small like errors and respond to every single details. So adding more data to your training sample is always a good idea. It's just that it's costly. If you're doing supervised learning, you need to manually annotate true labels for every single X samples, and it takes money, it takes time, so it's hard to increase your training data indefinitely. So what you do is actually you do regularization a lot of times. So okay, so before we get to regularization, I said that I'll talk about the trade-off between using too many features and too small features. So this is it. So there's something called curse of dimensionality in classical machine learning. So one of the remedies for underfitting was to use more features. As I said, adding more features like eyes and nose and furs and ears and something like that. But linearly increasing your number of features leads to exponential number of required data to fill your space. So what I mean by that is, so I'm going to assume that all the features in your data set is like continuous features, like blood pressure or height or age, like they're continuous features. So if your feature is one dimension, if you use only one feature, then there's only one line here in your feature space, and it's easy to draw a line that separates between positive cases and negative cases. You just draw a line here, and that's it. So everything below 1.0 is class 0. Everything above 1.0 is class 1, and that's it. So that's easier to easier to determine the boundary function, but the boundary line. But if you use two features, then now your space has become a plane. There's feature 1 and there's feature 2. And now your samples have two-dimensional information. And in order to draw a separating line like this, or maybe a line like this, you need to have a more dense, you need your space to be denser than before. So what I mean by that is, if your space only consists of only a couple of samples like this, then there's too many lines you can draw. The line can be like this, the line can be like this, line can be like this. Like there are just too many freedom to your model. So you need to have a denser space to make a more informed decision and make a better boundary. Now the problem becomes worse when you go three-dimensional. So if you use 3 features like this, then now it's a cube like this. So so the space has become exponentially larger. So you need exponential more number of features to fill the space in order to draw a informed hyperplane. So this requirement becomes worse and worse and worse if you use more number of features. If you add more features, add more features, add more features. So that's what curse of dimensionality is. Now this curse of dimensionality still plays some role in modern deep learning. So there's still it's something that you still need to think about when you do modern deep learning, especially in NLP, because when you do like model machine translation or like question answering or or sentence generation, you're basically operating on English dictionary. So you need to define a dictionary first in order to train your model. And your dictionary can consist of your dictionary can consist of 1,000 words, 10,000 words, or maybe you can use a bigger dictionary and 2,000 words. And it'll probably, like dictionary of 10,000 words will cover less amount of English sentence compared to dictionary of 20,000 words. But if you use a dictionary of 1 million words, then it's just too much, because this dictionary will consist of all the typos, all the spelling errors, and all the weird emojis, and all the abbreviations. So it's just just too large a space to learn your model on. So you want to use a decent size of dictionary to get a better performance. So that's basically you're trying to control the size of the feature space. And that's why that all goes back. It all boils back to that. That boils back down to trying to avoid the curse of dimensionality. Like this is no go. This is no go. Maybe this is maybe this is like this is better. Maybe this is better. Something like this. All right, moving on. So regularization. So as I said, one of the ways to remedy overfitting model is to use regularization. And basically what regularization is restricting the freedom of your model, which is the same as downsizing your hypothesis space. So we're going back to the polynomial function of degree 15. So your function of degree 15 would look like this. W15, W14, all the way to W1, and there's bias term here. And you can write that as a, inner product. And it just, I didn't really calculate this, but it's usually the case that when your function is as extremely wiggly and squiggly as this, then your coefficients W15, W14, W1 has a very high value, high magnitude, basically. Because in order to take a curve as sharp as these, your coefficients need to be really, really large, like maybe thousands or maybe tens of thousands. So when you force your model so that your W's or your thetas to have smaller magnitudes, then it cannot have this much squiggliness. It can only, if you restrict your models, like W can only have values between maybe 10, negative 10 and 10. Like all the W's, the WI's can only have values between 10 and negative 10 and 10. Then maybe it'll look like this. So this is still squiggly, but it's not as extreme as the blue line, right? So you're regularizing your model by forcing your weights to have a a smaller value than before. So how you do that? How you force your model to have smaller coefficient magnitude is just using this L2 regularization. So if you expand this, it'll look like W15 squared plus W14 squared plus all the way down to W2 squared plus W1 squared. And then there's lambda over 2. So lambda decides how much you want to penalize your model for having a large W magnitude. So if you use a very high lambda, then your model will be really, really regularized. So it'll look almost like a line. If you use very small lambda, for example, if you use a lambda value of 0, if this is 0, then this whole term goes away, and then you're back to the original degree 15 polynomial function. So L2 regularization, this term lambda determines how much you want to penalize. And there's some other forms of regularization, like L1 regularization. So here, you're using absolute value to penalize W's from having a like high magnitude. And it's all magnitude actually, because W squared or W absolute is all like, it's just pertaining, you're only trying to address the magnitude, not the direction of the W. Whether it has a positive value, negative value, doesn't really matter. You just want to, regularize the magnitude of the value. And it's called, so these two will have different effect. So L1, L2 regularization, L1 regularization, they're all regularization, but it'll lead to a differently looking model. I won't go into detail. Maybe we'll have a chance to talk about that later. And there are other forms of regularization. They're like dropouts can be seen as a regularization, for example. So anything that restricts the freedom of your model is regularization. It doesn't have to be like L1 or L2. Anything that restricts the freedom, anything that downsizes hypothesis space is regularization. All right, so now we're done with kind of like the theory aspects of basic machine learning. Now we're going to some of the popular classifiers, because this course, today's topic is basic ML. I felt like I should introduce at least some of the popular classifiers. So let me start with logistic regression. So logistic regression is a very popularly used binary classifier in all domains, like any domain. So, and you can derive it from probability. So probability lies in a space of 0 to 1, because it can't, there's no negative probability or probability over 1. And you can transform it into something called odds. So what's like the odds of you winning a lottery, or what's the odds of seeing the head of the coin, something like that. It's basically a ratio between winning and losing. And if you put log in front of the odds, that becomes log of odds, and log of odds is called logit. And if you assume that the logit can be modeled linearly, then that becomes logistic regression. And you train logistic regression via gradient descent. So yeah, here what this figure depicts what logistic regression is actually. So your probability of winning or seeing the head of the coin, your probability lies in this range, 0 to 1, but your logit, so this is logit, sorry. So this is your probability axis, this is your logit axis. Your logit can take values, any value between positive infinity to negative infinity. So you're basically transforming your probability space into a real number space. And then your logit, which is like this, you're basically assuming that you can model it linearly. So W transpose X plus B, or let me just stick to my original denotation, theta transpose X plus B. And if you put the log on the other side, then P negative 1P, P1 minus P becomes exponential of theta transpose X plus B. And then you rearrange some terms, then your P, becomes 1 over 1 plus e to the minus theta transpose X plus B. So this is your logistic regression expression. So we started from the probability and then we arrived here. So that's what logistic regression is. Moving on to support vector machines. So this is also very, very popular. It was proposed in the mid-90s, 1995, I think, and then it was like one of the go-to classifiers until deep learning came along. So even until like late 2000s, people are still using support vector machines very, very often. It's a very robust classifier. And why is it robust? Because why is it so powerful? Why does it generalize so well to unseen data? It's because the objective of support vector machine is maximizing the margin, which is the important concept here, margin between two classes. So a margin is a distance between samples from its boundary. So this is a decision boundary here, and the distance between the decision boundary and the closest samples is called margin. So this is margin. And by maximizing the margin, you're guaranteeing that your derived classifier will generalize well to unseen data sets. So because if you think about it, there can be a million different decision boundaries in this example. Like this is a correct decision boundary. This is also a good decision boundary. This Like there can be infinite number of decision boundaries, but there can be only one decision boundary. Well, I'm not sure if yeah, there can be only one because this is quadratic programming. So this, but there can be only one true decision boundary that maximizes the margin between the samples and the decision boundary itself. So you train it using a constrained optimization, and you do it by something called Lagrange multiplier. And to be more technically correct, you're using something called KKT condition. And I won't go into detail like how you derive all these. This is a bit complex. But these days, you don't have to even use this like mathematical techniques to learn support vector machine models. These days, you just use gradient descent with something called hinge loss. So there was a cross entropy loss. There was mean squared error loss. Hinge loss is another type of loss. So well, if you use hinge loss, you'll get something very similar to SVM actually. All right, moving on to decision trees. So decision tree is also another popular classifier. This is exactly what it says. It's a tree of decision tree. It's a tree that helps you make a decision. So this is an animal classifier, and you put some animal information here. Animal information, and if it has feather, you take this route. If it can fly, you take this route, and it's a hawk. If it cannot fly, it's a penguin. If it does not have feather and it does not have fins, then it's a bear. Something like this. And you use something called CART algorithm to derive this decision tree. So you have a training sample, and then if you use CART algorithm on that training sample, you'll get a nice looking tree like this. I'm not really an expert on trees, so I can't really explain what the CART algorithm is, but it's just suffice to know that there's some algorithm that you can always use, which is a very robust algorithm. All right, moving on. So ensemble so these are individual classifier, like logistic regression, support vector machine, decision tree. They're individual classifier, but you can actually pull multiple classifiers together to get an improved performance. So that is what ensemble is. And there are two popular methods for ensemble, which is bagging and boosting. And I'll first explain what bagging is. So bagging, and there are two ways to do bagging, but let me just give an example on the first method. First method is you have a training sample, you have a training set here, and then you sample a subset of the training sample multiple times. So this is a subset, this is a subset, this is a subset, and you randomly randomly sample a subset. So they will all be different. Well, I mean, they will be like slightly different from one another. Like this and this and this and this will all be a bit different. And then you have n subsamples, and you train n classifiers on these individual subsamples. And then once you've trained it, you have n classifiers. And when you have when you have a test set that none of these classifiers have unseen before, when you give the test set to the classifiers, they'll all give different answers, like slightly different answers, because they were all trained on different subset of a training set. So they'll give slightly different answers to the individual test set, and you pull them together, and then you do a majority vote. Maybe you do averaging to get the final answer. So that's what bagging is. And just compared to just using one classifier trained on the entire training set, breaking down into multiple subset and then training multiple classifier gives you better performance. So that's bagging. And boosting is a bit different. So boosting, you still use n different classifiers, but now you kind of chain it like a daisy chain. So there's the original data set here, and then you train a simple classifier on the original data set. And on some samples, it'll do a good job. On some other samples, it'll do a bad job. And you only take the ones that this classifier predicted incorrectly. You push them into the next classifier. So next classifier is only trained on the samples that the first classifier got wrong, and then the second classifier will do a good job on some subsample, and then it'll still make some errors. So the next classifier only works on the errors again. So you do this again and again and again. So you just do this chain where the k+1 classifier only works on the kth classifier's errors. And then once you've done this, then you have like an ensemble of classifiers again that work in a chain, and then you do averaging, or you do a chaining to get the final prediction. So that's boosting. And both boosting and bagging, they're like both, like all ensemble methods are very, it's a guaranteed method to squeeze out a couple more like accuracy percentages. Like if you're into like a challenge, or if you're into a contest or hackathon and you want to really, get a good performance, get a good accuracy, it's always nice idea to use ensembles. All right, so that was classifier and ensemble. Now I think we have only a couple more slides to go, which is clustering. So clustering, as I said, is an unsupervised method. So you're learning the distribution, like how the data are distributed, and you're trying to learn a coherent cluster on your data set. So popular clustering method is k-means clustering. So here, what k is the number of clusters that you have to predefine. So the number of clusters you have to define before you actually run the clustering algorithm. And it's all heuristics. Depending on the data, like if your data is really large and it's all like, it's very complex, then you might want to use like 20 clusters or 30 clusters. But if you use a very simple data set and you kind of know that there are only 2 classes or 2 clusters, then you can use 2 or 3. And the way it works is here, there's the, there's something called centroid, which is the center of a cluster. So there's the, in k-means, there's updating. Okay, I guess let me explain this first. So you update the centroid value, and then after that you update the membership of each sample. So let me give you an example. So here, the triangles, so there are 2 clusters basically. In this example, there are 2 clusters, so k equals 2. And then triangles here and here are the centroids, so they're the center of the cluster. And right now what's happening here is that it just so happens that this red dots here were assigned to the first cluster, the red cluster, and all the yellow dots here, yellow circles, were assigned to the second cluster, the yellow cluster here. And now that the cluster memberships are fixed, you update your centroid value. So the centroid should be the representative of your cluster. And since your cluster consists of 1, 2, 3, 4, 5 red circles, it should be located in the center here, which is the average of your cluster members. And in the same sense, your yellow circle, your yellow triangle should move towards here, which is the center or the average of all the yellow circles. So that's updating the centroid value. So your update, so this is updating the centroid. And once you've updated your centroids, then maybe there should be some changes to the membership as well. Now that your centroid is here, and now that your centroid is here, what was it here? Is here. Now that your centroid is here, you calculate the distance between the centroid, individual centroid, each centroid, and all the samples in your data set. So before it moved, so let me erase some of the here. So once a triangle has moved to this place, you calculate the distance between all the samples, between the sample and the centroid. And here, the yellow, I'm going to use blue for the yellow, like all this distance, like every single sample in your data set. And now that you can see that these yellow 2 circles here are closer to the red updated centroid compared to the yellow updated centroid. That's why the 2 red circles are now they have changed their teams. Now their membership is updated. So now they're in the red team compared to the yellow team before. So that's updating the membership. So membership update. This was centroid update. And then you repeat this process. Now that you've updated your membership, you recalculate your centroid, because now there was a change to the membership. Now it needs to move to the center here, which is the average of all the red circles. Now it's here, and again, like all the yellow centroid, the yellow triangle needs to be located in the center of the yellow circles, which is here. And then you do that again, and then you recalculate the membership and you update your membership, and then you recalculate the centroid, and then you update your membership. You do this again iteratively until there's no change to the membership. If there's no change to the membership, then there's no change to the centroid, and then which means that your cluster is kind of like, you know, settled to a satisfying place, which is here and here. So that's k-means clustering. And mixture of Gaussian is a generalization of k-means clustering. So you're putting a bit of a probabilistic spin on k-means. So k-means is a deterministic algorithm. Like the membership, like all the red circles here belong to the red group, and all the yellow circles here belong to the yellow group. But here it's a probability. So the dots here, they have a probability of being in the cluster 1, but they also have a probability of being in cluster 2. Like here, this guy has some non-zero probability of being in the cluster 1, but it also has a very small probability here being in the cluster 2. So it's a probability. And how you train your mixture of Gaussian, I mean, it's in the same sense, you need to set a number of, you need to predefine the number of Gaussians first, like k-means in the k. Like if in k-means, like you set the number of k's, and here you set the number of Gaussian distributions. Like here there are, I think there's a, so this is cluster 3, there is 3 Gaussian distributions, so it's like k equals 3. And how you train it is very similar to k-means clustering. In k-means clustering, you updated the centroid and you updated the membership. Here you update the mean and the standard deviation of the Gaussian, which is same as updating the centroid, and then you update the likelihood of your samples being in each cluster, which is updating the membership. So again, this is like iterative process. You update your mu and the sigma of the Gaussians, and which is the expectation, which is the expectation phase or expectation round, and then after that you update the likelihood of your samples being in each Gaussian, which is a maximization step. So expectation maximization, just like updating your centroid, updating your membership, updating your centroid, updating your membership. So there's like a almost one-to-one correspondence. I won't go into detail how EM is derived, which is a bit involved, but you can refer to PRML, the Pattern Recognition and Machine Learning textbook, which is a class, like a Bible of machine learning, written by Bishop. In that textbook, you can, you know, EM algorithm is very extensively explained. You can get a good understanding of it. All right. Okay, so this is the end of the week 2 theory class, which is basic machine learning. And so as I said, because of the morning's recording, it wasn't recorded. So this is the end of the recording, and I'll address the questions separately on the class, and I'll just write like I'll just use text to address each question from the students. All right, thank you very much, and I'll see you guys on Thursday.